Let's look at inverse functions. Let's take a look at these particular functions and we'll see what makes them inverses of each other. So I have f of x equals x plus 2 and g of x equals x minus 2. So let's calculate something like g composed with f of 10. You know that means we substitute the 10 into the f function first. So I would substitute 10 into this function, and notice 10 plus 2 is 12. So the result of f of 10 is 12. So now I need to find g of 12. So I substitute 12 into the g function, and we have 12 minus 2, and we get 10. So we had g composed with f of 10 equals 10. That almost looks like a dot that's really a circle. Remember, that's our composition symbol. So g composed with f of 10 was equal to 10. Well, let's do it with another value. How about g composed with f of 25? Well, again, we substitute 25 into the f function. 25 plus 2 is 27. And then we pop 27 into the g function. 27 minus 2 is 25. So again, in went 25 and out popped 25. Let's try this in reverse. Suppose we had f composed with g of 11. Now we're substituting 11 into the g function first. So let's go to our g function. 11 minus 2 is 9. So now we have f of 9. So now we move to the f function and pop 9 in. 9 plus 2 is 11. And it seems to be that whatever number we put in pops back out again. If that's true for every number in the domains of f and g, then the functions are called inverses of each other. And we can confirm that these are inverses by doing that composition. So f composed with g of x. Remember, that means g is our inner function. We take the g function and pop it into the f function. So we would have x minus 2 plus 2. And when you simplify, you get x. So we have confirmed that f composed with g of x is equal to x. But you do need to be able to compose it in the other direction and get the same result. So g composed with f of x. This time, remember, it's the f function that will be put into the g function. So we put x plus 2 in for x. So we have x plus 2 minus 2, and we end up with x. So we know now that f and g are called inverses. And this is the idea I'm using right here, right? If f composed with g of x equals x and g composed with f of x equals x, for all x's in the domain of g and all x's in the domain of f, then we have inverses of each other. Let me mention something else about inverses. Let's look at their graphs. I've already taken the time to graph these two functions. This is the function f, and this is the function g. If I make these values 2 and negative 2, then we draw a line right down the middle on the through y equals x right here. The y-intercept, notice right here, I had to change it. I had changed my y-intercepts. So now here's my y-intercept of 2 here, slope of 1. Y-intercept of negative 2, slope of 1. And notice these two lines are mirror images across the line y equals x. And if two functions are inverses, they will always be mirror images across the line y equals x. Let me mention one more thing. Let's talk about the notation. When we know that functions are inverses, we use inverse notation. So instead of saying that this is f and g, if I know their inverses, instead of writing g of x, I would write it as if f inverse of x equals x minus 2. And notice what I said, f inverse of x, that is not a -1 exponent. It's just our notation that says these two have this particular relationship, that one function will undo the other function. So I want to mention they are also mutually inverses of each other, so I could use g of x equals x minus 2, and I could say g inverse of x equals x plus 2. Again, they are mutually inverses of each other. Let's look at another function. Let's look at f of x equals x over 3 and g of x equals 3x. Now I hope you can look at these functions and think about what they would do. Notice the function f takes a number and divides by 3. The function g takes a number and multiplies by 3. And you may recognize that dividing by 3 and multiplying by 3 would undo each other, and you'll get right back where you started from. And we could test it with a particular value or two. F composed with g of 10, for example. We would put 10 into the g function, and we would get 30. We'd pop 30 into the f function, and we get right back to 10. We could compose them in the other order, g composed with f of 6, for example. Start with f of 6. 6 divided by 3 is 2. We'd pop that 2 into the g function, and we get right back to 6. This does not prove that they're inverses. It just gives us some confidence that perhaps they are. To show they're inverses, you do need to compose them in general. So I would have, if I were going to show these are inverses, I would have f composed with g of x. Do that calculation. So our g function gets popped into our f function. So here's our g function. It's going into our f function. So we would have 3x over 3. The 3's cancel, and we have x. So it's half done. Remember, you have to compose them in both directions to confirm that they're inverses. So this time the f function gets put into the g function. So x plus 3 is popped in right here. So 3 times x over 3. And again, the 3's cancel, and we end up with x. So they are, in fact, inverses of each other. Now, I wanted you to see the graphs of these two functions. I already have them done. This time I have the graphs labeled correctly. This one's the slope of 1/3. This is my f function. This is my g function. Now, I wanted you to see that in the previous example, the inverses were parallel to each other. That is not the way inverses are related all the time. They need to be mirror images across the line y equals x. And you'll notice right here, here's the line. Well, I should put a straight edge down so that I do it nicely. Here's the line y equals x right here. And you can see, in fact, they are mirror images. And by that, I mean, look at this. For any point on this graph of f, say this point right here, it's the point 6, 2. If we switch the 6, 2 and made it 2, 6, it is guaranteed to be on the graph of its inverse. You could do that with every point on this particular function. This is the point 3, 1. Its image point over here, 1, 3 is on the graph. negative, how about this one? -1, -3, its image point, -3, -1. For every point on the line or the function f, if we switch the roles of x and y, it will be on its inverse function. That ends up being an important idea. Let's look at then a picture of a function that looks like this. Suppose we're to draw the inverse function and the function we're given is this. Now I don't even have an equation to look at, but remember what I just said, we switch the roles of x and y. So for this one right here, this point 0, 5, on its inverse, I know 5, 0 would lie on its inverse. This point right here is the point 5, 10, so I'm going to go to 10, 5, and I know it would be on its inverse. Additionally, I'm going to use the fact that y equals x is right here. Let's put it in. Y equals x is the line right here. And they would be mirror images across that line. So I often turn my paper. It makes it a little bit easier for me to see if I'm drawing an inverse. So I'm looking at this. I know these two points will be connected this way. And I'm just drawing it freehand. I know this point is on the line y equals x, so it will stay right there. And now when I look at it, they look just about like they're mirror images across the line y equals x. Ooh, mine is a little bit too steep right here. That's in fact a big deal. It shouldn't be that steep. It should be going off at an angle. Ooh, that's a very big deal. So because of the point I'm going to make next, my scale is just a little bit off. This was relatively flat. This is relatively steep, but it is not vertical. But I hope now you see that they seem to be mirror images. Don't look at that vertical piece. Mirror images across the line y equals x. Kind of steep, but not vertical. So here's the next question I want to investigate. Does every function have an inverse? And we're going to consider f of x equals x squared. And I hope you know that that's a parabola if we look at its graph. So let's sketch it. Now, if we were going to draw its inverse, right, we know it's a mirror image across this line. So let me do my best. I have a parabola looking like this. I'm going to turn my paper and try to do the same thing here. And it looks like this. So I hope you see that those seem to be mirror images across the line y equals f. So here is f, and here is what I have drawn as potentially f inverse. But here's the part that I want you really to take note of. This cannot be an inverse function, but it's the only potential inverse function of this function, f of x equals x squared. And yet it's not a function itself. Notice this fails the vertical line test. So this graph right here does not represent a function. Not a function. Because it fails our vertical line test. Vertical line test. So in fact, f of x equals x squared does not have an inverse function. Does not have an inverse function. because the only potential one that we had wasn't a function at all. So that brings me to this important question. How will I know if a function has an inverse? I don't want to go on a wild goose chase looking for an inverse when an inverse function doesn't actually exist. And here's the key. Look at where these points came from on the original graph. This point, its image point is right here. Let me draw it. This point right across the line y equals x is right here. This point right here comes from this point over here. These 2 points are in the same horizontal line. And when you fold this paper over on the line y equals x, this horizontal line became this vertical line. If a function fails what we call the horizontal line test, it will not have an inverse function. So we have what's called the horizontal line test. Works just like the vertical line test, except it's a test to see if your function has an inverse. So right here, because these 2 points were in the same horizontal line, I knew f of x equals x squared did not have an inverse. So let's consider this function. We'll do 2 of them. And for each, the question is, does the function have an inverse? Well, we can simply look at the graph for these 2 functions because we know what the graphs look like. So let's start with the absolute value of x. I hope you remember that it looks like this. It looks like a V. Remember, with one part having slope 1 and one having a slope of -1. Notice if I draw a horizontal line right here, it would hit in 2 points. So we say this fails the horizontal line test. Fails the horizontal line test. So that means f does not have an inverse function. And one more piece of vocabulary that I haven't mentioned is that we say this function is not one-to-one. F is not a one-to-one function. A one-to-one function means there is a one-to-one correspondence between x values and y values. Here at this y value of, say, 5, there would be 2 different x values giving you that y value. At 5, you would get 5, and -5, you would get 5. So there is not a one-to-one function. This is not a one-to-one function. These 3 things go together. So let's look at our next one. F of x equals x cubed. I hope you remember what this looks like. Here's our y equals x cubed graph. It looks like this. And you'll notice no matter where we draw a horizontal line, it never hits the graph in more than one place. Even here, it doesn't actually go horizontal. It flattens out, but there are no 2 points in the same horizontal line. So this one passes the horizontal line test. Let's see if we can squeeze it in. Passes the horizontal line test. So it does have an inverse function. And we say that f is a one-to-one function. So there is a one-to-one correspondence between x values and y values. For any value here, if this were 8, I'd have one y value of 2. 2 gives me 8, one-to-one correspondence. And no matter what point I grab, you'll find that one-to-one correspondence. on this particular function. Let's move on. We already saw that we could find the inverse function if we had a graph. Suppose now that we have an equation like this, f of x equals 2x plus 11. Sometimes people just guess and say, well, I can guess what the inverse would be. So let's try that strategy. We'll guess, and I'll just tell you a common guess for people. I'm going to use g because we do not know if it's the inverse. Let's just make a guess. This is very common. People see a multiplication with 2, so they decide that dividing by 2 would undo that. There's a plus 11 and make it a minus 11. So this is a common guess. Let's see if in fact they're inverses. We know that the test would be f composed with g of x. So I'm going to put this g function into the f function. So we have 2 times x over 2 minus 11. I popped that in right here, and then we still have the plus 11 part. So this was our g function going right in here to the f function. And remember, we're trying to see if this is in fact the inverse. We distribute the 2 and we get x, distribute the 2 and we get negative 22 plus 11. We get x minus 11. So I don't need to compose them the other direction even. What I know is they're not inverses. So the guessing strategy, unless the function is particularly simple, often isn't very effective. So that begs the question, if f of x equals 2x plus 11, what's the strategy to find if f of x equals 2x plus 11? Let's do this again and have a strategy for it. And the key to knowing how to find the inverse is right here. Let me bring you back to this graph. Remember when we had these two inverse functions that I could have called f and f inverse or g and g inverse? We did find they were inverses. I mentioned that for every point on f, if you switched the roles of x and y, the point would exist on g and vice versa. So the roles of x and y switch. The domain becomes the range becomes the domain. For every x value here, it becomes a y value. So if we're trying to find the inverse, we're going to switch the roles of x and y. Remember, the f of x is playing the role of y. So here's my y, here's my x. To find the inverse, I switch those roles. My y becomes my x, and my x becomes my y. And then we solve for y. So let's subtract 11. And now divide by 2, and notice we're going to divide the entire function by 2, both sides, and we get y equals x minus 11 over 2. So that common guess that people have wasn't too bad. There's still a 2 involved and 11 involved, but we didn't divide the entire x minus 11 by 2 in our guess. So here is our inverse. Let's write it with our inverse notation. So we would say f inverse of x. When you're writing an equation, make sure you use that function notation. We're going to put that x part in there. F inverse of x equals x minus 11 over 2. And you could compose these. I'm not going to take the time to, but you could compose these and see that you would get an x if you composed them in each direction. So let's practice finding the inverse for some other functions. Let's do this one next. So for the inverse, remember there are 2 steps: switching x and y, and then solving for y. So here's my y, it becomes an x. Here's my x, it becomes a y. And I solve for y. You can subtract 5 or multiply by 2, whichever you prefer first. I'll subtract 5. And remember, now we need to multiply by 2. We'll multiply by 2 on both sides. So we have 2x minus 10 equals, and our 2's cancel, and we have y. And again, we're going to use our function notation to answer the question. So f inverse of x equals 2x minus 10. Let's do another one. The next function we'll find the inverse of will be this one. F of x equals 3x cubed minus 6. Remember the 2 steps. Switch x and y, solve for y. So here we go. We switch x and y. Here's our y, it becomes our x. Here's our x, it becomes our y. And now we solve for y. So let's add 6. We'll divide by 3. And notice that 3 and the 6 don't cancel because there's no common factor. And now we'll take the cube root of both sides. Remember, when you're taking the cube root, you do not put a plus or minus in. If you're taking an even root, if you have a square root or a fourth root, you do. But on a cube root, you do not. So we have y equals the cube root of x plus 6 divided by 3. Make sure that 3 is underneath that radical sign. So let's present that. F inverse of x equals the cube root of x plus 6 over 3. Here's our next one. Let's find the inverse function if this is our function. And it's nice, there are 2 steps. 1, switch x and y. 2, solve for y. To find the inverse. Doesn't matter what the functions look like, so here we go. We'll switch x and y, so x equals the 5th root of y plus 4 divided by 2. Make sure when you write something like this down, you're not sloppy. That radical sign stopped right here before our fraction bar. Unlike the previous one where the radical sign went all the way down to the bottom of the fraction. So let's say we're solving for y now. Let's multiply by 2 to take care of the fractions. So we have 2x equals the 5th root of y plus 4. We're going to raise both sides to the 5th power. So we'll have 32. Don't forget that 2 gets raised to the 5th power as well. 32x to the 5th equals y plus 4. And y equals, let's subtract the 4, 32x to the 5th minus 4. So f inverse of x equals 32x to the 5th minus 4. I want to mention a couple of things. One is, I am not asking you to find the inverse function of a function that doesn't have an inverse. All of the functions I'm presenting have inverse functions. So I'm not sending you on a wild goose chase. And also on some functions, when you're finding the inverse, you have to be careful about the domains. I haven't given you any where that's a particular challenge in these examples. That would be a discussion on another video. I'm just focusing on this idea, and we're doing some basic ones. Let's do one more. Here's our function, and we're going to find the inverse. So, step 1, we switch x and y, so we have x equals 1 minus 3y over, make sure you change both of those x's to y's, 5y plus 22. And now we're on to step 2, which could take a few lines to get there. We're solving for y. Let's clear out our fractions by multiplying by 5y plus 22. So these cancel. And we'll distribute our x. So we have 5xy plus 22x equals 1 minus 3y. Don't lose sight of the goal. The goal is to solve for y. Sometimes halfway through, people forget what they're doing and they solve for x, and they end up right back where they started from. But our job is to solve for y. I notice I have a y here and a y here. I need the y's on the same side, so I'm going to add 3y so that the 3y will be on the left. So I have 5xy plus 3y. And at the same time, I'm looking at this 22x. I don't want it on the same side with these terms that contain y, so I'm going to subtract 22x. So my equation now looks like this. All the terms with the y on the left, all the terms without the y on the right. And sometimes this is where people forget what to do. There is a common factor of y. This is the key. Factor out that y, and we have y times 5x plus 3 equals 1 minus 22x. And now we can divide by 5x plus 3. Divide by 5x plus 3. So our y is equal to 1 minus 22x over 5x plus 3. And let's just write that nicely with our function notation. So f inverse of x equals 1 minus 22x over 5x plus 3. I hope you'll go practice finding some inverse functions.